Hi guys! In today's video, we're going to talk about non-deterministic algorithms. But before getting into the action, let's match our expectations. My videos depend on the wisdom of the crowd, a topic that really fascinates me. Since I'm studying this topic by myself, there might be an occasional mistake in what I say. Please let me know in the comment section below if you wish to correct me, of course. I promise to read all comments and re-upload if necessary. Together, we can answer tough questions in a better way. Also, please subscribe to my channel. I tend to upload many videos on this topic. To understand the idea of non-deterministic algorithms, we will discuss on deterministic algorithms as well and learn the differences between the two and finally challenge ourselves with a made-up term. Let's jump right into it. Alright, non-deterministic algorithms. Deterministic algorithm. Given a particular input, the deterministic algorithm will always produce the same input and pass through the same steps. Non-deterministic algorithm. Given a particular input, the non-deterministic algorithm might produce different outputs and pass through different steps. In other words, when handling deterministic algorithms, we can be confident in the given output. In non-deterministic algorithms, on the other hand, we might get unlucky with the output of the algorithm, and a second run on the exact same input would yield a different result, and so some runs would yield completely wrong outputs. To practice the notion of non-deterministic algorithms, we would come with a made-up term called strongly decisive non-deterministic algorithm. Such algorithms return one of three answers: yes, no, or perhaps. In contrary to the classic non-deterministic decisive algorithm, which only returns one of two answers, yes or no. We would call such a made-up algorithm A. Additionally, given a decision problem S that algorithm A solves, we know that 1. If input X is in S, then any run of algorithm A on input X returns the answer yes or perhaps, but in no way it returns no, in contrary to the classic decisive non-deterministic algorithm, which might return no in such a scenario. We are also guaranteed that there is a run which returns yes in such a scenario. If input X is not in S, then any run of algorithm A on input X returns the answer no or perhaps, but in no way yes, in contrary to the classic decisive non-deterministic algorithm, which might return yes in such a scenario. We are also guaranteed that there is a run which returns no in such a scenario. In other words, algorithm A never returns an invalid answer, and for any input there is a run in which we are guaranteed a correct answer. We would prove that if problem S belongs to the conjunction of classes NP and CONP, marked as the following, then there is a strongly decisive non-deterministic algorithm A that solves the problem. First direction. Assume that there is a strongly decisive non-deterministic algorithm A that solves problem S. We would prove that S belongs to NP and to CONP as well, and therefore S is in the conjunction of NP and CONP. We'll start with S in NP. If problem S has a polynomial non-deterministic algorithm that solves it, then according to the definition of complexity class NP, S is in NP. According to the definition of the strongly decisive non-deterministic algorithm AX, there is a run that returns yes if input X is in S, and a run that returns no if input X is not in S. Because this definition satisfies the requirement of non-deterministic algorithm, we can say that S is in NP. Now we'll show that S is in CONP. We would recall that a problem is said to be in the complexity class CONP if we can check if a given input does not belong to S in a polynomial time. We would build a verifier for algorithm AX that acts as the following. If AX returned yes or perhaps, then the verifier returns no. the verifier returns yes if and only if AX returned no. Therefore, we get a positive answer only if X does not belong to X. The round of the verifier is polynomial bounded because it used a polynomial algorithm AX, and therefore S is also in the class CoNP. Therefore, S is in the conjunction of NP and CoNP, second direction. Assume that S in the conjunction of NP and CoNP. We would prove that there is a strongly decisive non-deterministic algorithm that solves problem S. S is in NP, and therefore there is a non-deterministic algorithm that solves S. We would mark it as A. S is also in CoNP, therefore the complement of S is in NP. Therefore, there is a non-deterministic algorithm that solves the complement of S. We would call it B. We would now define a strongly decisive non-deterministic algorithm that solves problem S. We would call it C. Given an input X, algorithm C will run both algorithm A and algorithm B on the input X and would return the following value. If both A and B return no, then algorithm C will return perhaps. If algorithm A returned yes, then C will return yes. If algorithm B returned yes, then algorithm C will return no. Analysis of time complexity of algorithm C. Notice that algorithm C runs two polynomial bounded algorithms. Hence, algorithm C is also polynomial bounded. Correctness of algorithm C. If the input X is a valid answer for the problem S, then it is not a valid answer for the complement problem as complement. Since we assume both problems are in complexity class NP, then there is a classic non-deterministic decisive algorithm that solves them. According to the definition of such an algorithm, for an input in the problem the algorithm solves, there is a guaranteed run that returns yes, and for an input not in the problem, all ones return no. If both algorithms return no, then we cannot conclude anything, and therefore we return perhaps. If one of the algorithms, A or B, returned yes, however, then we know for sure that the other returned no, and therefore algorithm C can trust the positive answer that it receives from either A or B, and proceed with either steps 2 or 3. In conclusion, we have seen that if problem S is in the conjunction of complexity classes NP and CoNP, then there is a strongly decisive non-deterministic algorithm that solves problem S. From both directions, we can conclude that S is in the conjunction of classes NP and CoNP if and only if there is a strongly decisive non-deterministic algorithm that solves problem S. Well, that's about it. I hope you learned something new from this video, and please comment below with your thoughts. First degree studies in university are all about social studies, and this project comes to encourage that. Please subscribe to my channel. Until next time, bye bye!